Hi everyone. Today, plan. We're going to finish up talking about 4-1. Do a little bit of what we did last time and then close it out with a couple more examples. We'll do a 4-1 classwork assignment. Like 10 minutes, it should be a shorty, it's only like 2 types of questions. We'll dip our toe into 4-3, we'll do a little bit in there, and then we'll do a classwork assignment at the end there, and that's our day. Okay? Sounds pretty good. Not bad, right? Alright. So,
No, you're done. You're already. Oh my God, this is terrible. No, you're You're not even like if she. I'm not even joking.
I want to start just talking about converting between radian and degrees, right? To do this, what's the key thing to remember? What's the conversion factor from radians to degrees? 180 degrees is equal to pi radians. Perfect. If you don't think you're going to remember that, something we should memorize. If you don't think that's a realistic option for you, or you don't trust yourself to memorize that, where should it go? Onto your half sheet of notes, so that come a test time you have that and you're not relying just on your memory, that you have some reference to look it up on. Okay. So let's say we have 120 degrees. We want to convert this into radians. We want to treat this just like a unit conversion problem from our chemistry class. So I'm going to turn 180 degrees into a fraction. Because degrees are on top, where does degrees have to go on my conversion factor? Bottom. So on bottom, I'm going to write 180 degrees, and on top then, pi radians. Everybody feel good? Okay. The degrees cancel. And I'm going to try to reduce the 120 over 180. So real quick, I can look at that and go, okay, well, they both have a factor 10 in them, so let's reduce the 0 off the ends. Do we see any other factor in common between 12 and 18? 6. Great. 12 divided by 6 is 2. 18 divided by 6 is 3. So then if I multiply across, I have 2 times pi on top and 1 times 3 on the bottom. So my answer there would be 2 pi over 3 radians. Now I'm going to stop writing radians at the end of things that are radians. Typically we don't do that for very long. We just recognize if it has a degree symbol, it's degrees. If it's an angle without the degree symbol, it must be a radian. Everybody's okay? Okay. I'll keep writing it on the conversion factor or whatever, but like at these end answers, I'm probably going to quit. Okay. What if we want to go the opposite direction? So maybe we have 13 pi over 12 radians. And again, we can think about that radians unit on the top. So when we do our conversion factor, where does the radian unit have to go? On the bottom. So we'll write pi radians on the bottom. And 180 degrees on top. Radians cancels with radians. Pi cancels the pi. And then we just have to reduce 13 over 12 times 180. Well, I know there's nothing in common between 13 and 12 because 13 is prime, right? How about between 12 and 180? Are there any common factors there? for sure 6, right? Should be easy to see that. So I know 6 goes into 18 3 times, so it goes into 180 30 times. Everybody's good with that? Mental math. Now 2 and 30. Anything in common there? 2. Okay, so that just gets nuked down. And 13 times 15 is, oh boy, is he? 100 and, it's too many classes. I'm not mental mathing yet. I give up. 195. Does everybody feel okay there? And what we did? Okay. Now, the other thing that we saw yesterday when we were doing this was this relationship, that an angle measure is equal to, or angle measure in radians is equal to arc length over radius, right? So I'm going to write theta for my angle measure. And to indicate that it's in radians as opposed to degrees, I'm going to put a little subscript r on that. The r stands for radians. And then arc length, I'm going to use the letter S. And radius, I'm going to use the lowercase letter r. Everybody's okay here? Yes?
Wait, so that's another way to write the arc length over.
This is just the same formula with symbols
Oh.
instead of words. That's all I'm doing. I just invented some symbols to take these place.
Okay.
These are the kind of the traditional symbols we use for these quantities in a course like this.
Okay.
So arc length is traditionally S, radius is traditionally R, angles are traditionally Greek letters, oftentimes theta. Okay. So if I wanted to, like I could multiply both sides of this equation by R. And could write it this way, right? That's just me rearranging the same equation. Nothing new has happened. Everybody agree? So what this has done is it gives me an equation for arc length in terms of a radius and an angle. Everybody's okay? What's the only catch here? Is that angle must be in radians. What would I do if the angle was in degrees? I'd have to convert it to radians, right? So if I have an angle in degrees, I'd have to multiply it by pi over 180, and that would give me an angle in radians, right? Everybody agree with that? So the other option then is I could say S is equal to R times an angle in degrees times pi over 180. Now I have a formula in terms of degrees and a formula in terms of radians. So these are the two takeaways. This is how there's a formula to find arc length. One version requires an angle in radians, the other requires an angle in degrees. Notice that they're the same formula, it's just that the angle in degrees, we've applied that conversion factor to it and then dropped it into place. Is everybody okay? All right. So that's what these two things are saying. That's exactly what we just went through together. I'm not gonna belabor this because it's the same thing as up there. Is everybody okay? I'm gonna scoot past this just to the examples. This first example says, find the perimeter of a 60-degree slice of a large pizza. So when we hear the term perimeter, what does a perimeter mean? What are we asking for if we're looking for a perimeter? Just in words. It's the distance around, right? The outside border. Everybody's okay? So if I look at this picture, my perimeter would be 7 plus S plus 7. Everybody agree? Now, when you slice a circular pizza, where do all those points of those slices meet? In the center of the pizza, right? Ideally, I mean, like, you know, we've all had shamefully cut pieces before, but like, that's where they're supposed to be hitting, right? So, this is a theta. This is a radius. This is an arc length, right? What do we need to solve this perimeter? We need this arc length. Do we have a formula that relates arc length to radius and theta? Where did you go? Oh my goodness. It's back here. There it is. Right, these guys, right here. Which one do I want to use? The one with the angles in radians or the one with the angle in degrees?
Degrees.
In degrees. Why degrees? Because the problem was in 60 degrees, right? It was given to me that way in the problem. So let's go back. Ugh. Okay. So we know that S is equal to R theta D times pi over 180. Is it okay that I consolidate that formula into like just one fraction instead of something times a fraction? Still the same formula, I just wrote it a little differently. Okay. So if I fill in, what do we have? Radius is 7. Theta is 60. Pi over 180, right? Everybody's okay? Finn.
Oh wait, is the D to show that the theta is in degrees?
Yes. Yeah, so that's like a subscript on the theta. That's just me putting it there to remind you that like, you use the right formula.
Okay, got it.
Okay. Because like, the number one issue students have is they use the wrong formula, right? So I try to put a little subscript down there to remind myself. All right, let's get this into a calculator then. There. So I did 7 plus. Do you know how to remember how to get the horizontal fraction bar in your calculator? So to get that horizontal fraction bar, you just press the green alpha button and then the variable button right next to it. So notice I typed in my answer to the perimeter all in one line, just for the trying to make my life a little bit easier. I like to use the horizontal fraction bar because then I don't have to worry about parentheses. I can just write it down how it looks like on my sheet of paper into the calculator. So the answer I'd report might be like 21.33. Everybody feel okay there? See lots of people typing it in for themselves. And I think the unit there should be inches, right? Because the radius was inches.
Oh, it says 60.
Yeah. Yes, Ruby.
It's just 7 times 60.
How do you look up from my calculator? It doesn't do that. It makes like an X.
Did you press alpha
Oh,
first?
it does 7 and then
Okay,
and then plus another 7.
that's fine.
The
So
S
you
is
do
that equation.
alpha y equals.
What? Yeah.
Right. But if you look at what I did 7 plus this plus 7. Right, I did the whole perimeter. Not just so to get the horizontal fraction, just y equals.
Thanks.
Oh, I know.
You remember when you submit your Because you turned it, you know.
Oh, you just like
Right, so when I typed in the calculator,
Are we changing right now? I don't even know
so I
what
did
it said.
7
I don't
plus
remember what it said either.
this
It must have been one of those.
plus
That's how I drink my podcast with that. Actually, it's not. You were able to.
Alright,
Yeah. See you laugh, then you should drink water.
on to the next one. Alright.
Stop laughing.
This says that the running lanes at Emory Sears Track at Bluffton College are 1 meter wide. The inside radius of lane 1 is 33 meters, and the inside radius of lane 2 is 34 meters. How much longer is lane 1 than lane 1 around one turn? Huh. So what it's saying, what is, if I look at the picture they provided for us, if you're running along a curve and you want to go be as most efficient as possible, where would you be running?
Lane 1.
On the inside of the curve, right? So the shortest distance I can travel in lane 1 would be like this distance. Everybody agree? I'm going to call this distance S1. And the shortest distance I could travel running in lane 2 would be the inside of lane 2. So it would be that distance. I'm going to call that distance S2. Everybody feel okay so far? So the question asks, how much longer do I run in lane 2 than lane 1? So what I'm looking for is the difference between those two distances. Does everybody feel okay so far? Okay. Now, if I look at this, I'm going to change the color real quick here. Come on now, just behave. If you look at this picture, hopefully you recognize that like this is just like a circular track, right? Or at least this portion of the track could be part of a circle. You guys agree? Okay. So these distances, S1 and S2, are arc lengths. Agreed? Okay. So if I were to draw the center of the circle, looks like it'd be right there. And this angle here would be the theta. Everybody agree? How many degrees is that theta?
180.
180. Okay. Why am I asking for trying to find out this angle? So I can use that arc length formula from before, right? Because we point out that these were arc lengths. Yeah, everybody's okay? If I do the same thing for the green circle, what's that angle? Still 180, right? It's the same angle for both circles because they're concentric. You know what concentric means again? They share the same center. Okay. So I'm just gonna write that angle one time, and I'm gonna get rid of all this extra green mumbo jumbo just to clean this thing up a little bit. Everybody's okay? Okay, so this theta is the same in the green as it is in the red. That's the takeaway. Okay, the last piece I need for my formula for arc length is a radius, right? Well, I'm given that, aren't I? The radius for the red circle was 33, and for the green circle it's 34, so I'll call that R1 and R2. Does everybody feel okay?
Yes.
Okay. So I know in general that S is equal to, which formula do I want to use for S? Radian or degree? Degree, because this is, we said this is in degrees. Could I convert this into radians to make it a little cleaner? Is it a really easy conversion? Yeah? What is 180 degrees in radians? Pi, right? Because that's the conversion factor. It's like the easiest possible conversion factor or conversion to do because it's literally just the conversion factor. I mean, maybe it's second easiest. 0 is probably the easiest, right? Like 0 something converts to 0. No, anyways. Okay, same as pi radian. So let's use the radian version because the formula is simpler. Will I get the same answer if I did the degree version? Yeah. Is the radian formula got less going on in it? Yeah, that's why I'm choosing to do this. You get the same answer if you did it with degrees using the degree formula. I'm going to do it with radians and use the radian formula because it's a little less writing. Okay. Right, so that's our formula that we're going to use. So for S2, my radius is 34, and my R is, or my theta is pi. For S1, my radius is 33, and my theta is still pi. So I have 34 pi minus 33 pi, which is just equal to 1 pi. Done. So the key was recognizing that what you need to find was the difference in two arc lengths, and just using your arc length formula to find each of the arc lengths and subtracting them.
What's the thing after the pi?
That's meters, because I think that the radiuses were given us in meters, so that's just the name of the unit. What do you guys think? No big deal, right? Hopefully not. Okay, pause here. What I'm going to ask you guys to do for your first set of classwork today is, let me get the sample, 4th hour. So what I'm going to ask you to do is the 4.1 classwork. There's 2 types of problems, radians to degrees and degrees to radians. So notice on the radian to degree problems, they might ask you to round. This one doesn't because the answer comes out to be a whole number. If it's going to be a decimal, though, they might ask you to round to some decimal place. That's okay. You can have a decimal answer, particularly if it says round to the nearest whatever. You know you're going to probably get a decimal answer. Is everybody okay there? Okay. And in degrees to radians, it's going to ask to express our answer in simplest form. That means it's going to, they want a reduced fraction with a pi in it, is what your answer should look like, okay? I'm going to give you guys 10 minutes to work on this, and then we're going to regroup and kind of continue. We'll have still more time at the end if you don't finish in your 10 minutes, but
If you have a question, I'll help you.
I would say that in general, 2/3 of second hour finished in 10 minutes at least, maybe more. So should be okay. these should realistically be like less than 1 minute problems once you kind of got the hang of it. So it's just like, all we're doing is converting, so just multiplying by the conversion factor appropriately. The hardest part is cleaning your answer. Okay. So go ahead and work on this, it'll take about 10 minutes and then regroup and talk about a little bit more new stuff.
Wait, it's 4.3.
This is 4.1 classwork is what you should be working on. Yes, CW for classwork.
Oh my gosh. Do you have an extra number by any chance?
Yeah, you can grab one from the sack, you can give me an ID or set of keys or something. Cool. Thank you, sir.
I guess my dog's spell
It's just like, you get all the fun stuff.
What do you mean?
Being sarcastic.
No,
Like it's giving you all. Oh, yeah, okay, sorry, you got it, I was not, that's fine, don't listen to me.
It's Christmas. Okay, wait. Do the show.
This is more like this one,
And then,
right, you're starting with gradients.
oh, that's a good idea. That's what I did.
Yeah, let's be great, so sure.
Oh my gosh. Why is it
So
4?
you multiply this guy by
Okay.
180 over pi, and then you'll reduce it and you get an answer.
Jack, it's not that
Or
hard.
you get an answer trees.
Are you doing
Do the same thing.
Hit me once. Hit me again.
Grab one. Okey dokey. That's all right.
Oh,
All right.
wait, what is this?
Hi.
Convergence actually.
Oh, okay. What's is radians? Wait, what is it? Example.
Hey, Jack, I'm back. Go ahead and say your workout.
We're just converting from radians
Oh,
to
right
degrees.
here.
Yes.
Oh my gosh, I'm very sorry.
That is okay. It's easier than you thought. right?
Yeah, I just, yeah.
Angle 6 radians to degree. Angle 6 to 7.
I'm just like, but there's no pi. Okay, so 5.5 is like my revision, so I have to.
Wait, I don't know why I cannot.
So that's not 5.1, it's just 5.5. So you're literally just doing like,
So now we go see that.
Radians and degrees.
Okay, I saw that.
like, that's it.
Okay.
Like, it's easier when you get round your answer, because like, there's gonna be no fraction to mess with, there's no pies.
Okay.
It's just like, multiply it, decimal, round.
Yep. Okay, wait, let's try this.
Okay, so you have 4.5 radians. So we're gonna multiply that by the conversion. Since you have radians on top, what's gonna be on bottom?
I put 10 remaining.
Yeah, so you have to multiply by.
Do they have an example?
You're gonna pi
Oh,
radians
but
on
like
bottom.
all the ones with
Stop.
pi in them. And there's no
What's gonna be on top?
Alright, I figured it out. I didn't actually want to.
Like this? Yeah.
Second part is actually.
Do like it
Gives the answer,
What
it's rounded to the 10.
I put 200
What we do is take our calculator.
Okay, wait, Delta.
Bro, just
Yeah,
give
like,
it
I-
Actually, like a 47. Oh, yeah, how flashlight.
If it's going into your calculator, it's fine to put it. You don't have to. And then you just get the answer that's decimal and round it.
Right now,
It's fine.
How much was really 705 reduced to 47?
Oh, God.
It tells you the example.
I see how to do it.
You're right, I'll check out also.
I don't.
Yes.
Well, March 12th doesn't matter.
Oh my God, where's your ground everything?
Oh, I got it right.
Right, so you're not-
Not me being surprised. Oh, reduced to
Right, so the
radius.
direction says rounding to your standard.
We're gonna do the. You should drive. Are you driving this year? Remember when you were about to,
So it's just a-
your mom didn't stop? was gonna be awesome.
I feel like it's just
Is it a negative one?
Yeah, that's right.
Both of them are just.
Okay. But it's like a really big number. Oh.
Now put the pie back.
I just got signed.
Yes.
Good at this.
It's like, how simple is that? Like, use that machine. Yes, sir. Let's do this. So I'm just gonna ignore the pie.
I did my job.
Was that? Thank you.
One decimal place.
Oh, what? I got it really.
Don't say you didn't expect to call this.
Where?
I was on the wrong one the whole time.
This is just my personality. My personality is not your culture.
I'm so bad.
How's it going?
I was on the wrong one, so I was
Don't do that.
doing the wrong one.
That's probably why it's like, it's like anything you can do.
Yeah, I was kind of confused.
What? Now it looks like exactly.
Yeah.
Not number round.
Do you have like a super good kind of factors in there?
So, when you have 600 over 180, right, you're trying to find a common factor. What's that?
Yes. Wait, you sure you want the you can put it.
Like, I know it's not for me, but it's like.
But 600 over 180.
Wait, no.
So, the answer to you is yes. I do have a super easy way.
Well, now these problems will take like 2 seconds. So it'd be 1.
No, yeah, I got the same thing.
Tell me, wait, what's this something about?
No,
I figured it out.
I'm so confused. Can you help me? I don't want to do it.
Have you ever seen that one description? I remember
So
like
you
okay,
do
it's like
negative
Hello.
0.5. What's that, right?
Yeah, then it's going the other direction for the next step. Yes.
Oh, yeah. So you do that times, and then you divide by.
So I would
Oh,
just, so it isn't asking for an answer rounded to 10. I barely.
Oh, yeah. Thanks, Emily. I just can't do my decimals. No, I like you forgot what the points were. I thought it was so much. So I was like, oh, there's no points. Yeah, that's what I was thinking. Okay. My mom's like, okay,
Yeah,
don't do
that's
So, yikes.
what I would find offensive.
I don't think
I watched that.
I like dark humor, buddy.
Sure. I watched that too.
Oh, yeah. I saw 6 last year. The problem was 6 radiant degrees. We have that is
Number 480 over 180.
Oh, I was supposed to buy your shit, but it's supposed to work. Yeah, I did it, and I got like 2.6.
I'll give you just go back.
Yeah, that's fine. That's fine.
Okay.
Yeah.
Well, I think I'm
So,
No, I got two.
like,
Because you did
I-
It's actually like,
We're supposed to do this.
This is so August 20th, the right answer is a friend.
I understand. Now that I know how to round to the right place.
How many did you do? Like that?
Just that one.
Okay.
I know, but during the
so
whole
I
week,
can
I was
just
like,
like
what
split
did
and
you do?
disregard the pie.
Well, then now.
But I figured it out, I just
Not
forgot
pie.
since then.
The calculator won't do the reducing of the pie in there, but if you leave the pie out, it'll reduce the numbers and you just put the pie back out. Does that make sense? It's the easiest way to handle that.
You and you talk about this?
It's 8 over 2, but you have to put the pie up.
I've been saying this.
Wait.
That person is.
Joe, did I see you have a hand up?
They're using it for discrimination.
I know.
She's using it for
Wait, I
discrimination.
really like that.
Yes.
Yeah, I just.
Actually, it's not. Actually, it's
Don't stop.
Okay, so 5.
Come on. No, not you. I want you. Nope, that's it.
not
Here.
Okay,
So, if you guys remember back to geometry, what was the biggest angle you could draw in geometry? 180 degrees because it was a straight line, right? So like when I drew an angle like this, we always measure the smaller option. We never measure the bigger way, right? Do you remember this? Which means 180 was the biggest thing you could draw. We're going to fix that today. We're going to describe a new method of drawing angles that allows us to draw angles that are bigger than 180 degrees. Okay? So to do this, what we're going to do is we're going to fix our angle inside of the xy plane. So right, xy plane. We're going to put the vertex of our angle at the origin. That's the point 0, 0. One arm of our angle is going to lie on the positive x-axis, always. We call that the initial side. And then we're going to think about the other arm of our angle as like hinged at the origin. And we're going to let that, come on now, and we'll let that rotate however many degrees we need to, and that'll represent our angle. We call that arm of our angle that rotates, we call that the terminal side. So in this picture that we've drawn, we have our angle. We have our initial side. And then we start and we rotate that initial side to the end, and we call that the terminal side. Okay? If I were to estimate the size of this angle, from here to here is 90 degrees. How did you know that? One quadrant is always going to be 90 degrees because we know the xy axes meet at a right angle, right? Okay. Now I look over here. How much of a quadrant does this look like? About half, right? So maybe the whole thing then is 90 plus 45. Everybody's okay? Let's practice drawing some. Yeah? So let's do a 205. That's one that we couldn't draw in geometry, right? No way to draw that. We've now created a way to draw this. So we start vertex at the origin. Initial side on the positive x-axis. And then we start rotating. Basically, I'm going to be counting by 90s. So here's 0, 90, 180, and then how many more degrees do I have to do? 25 more, right? And 25 is just a little more than a quarter of the quadrant, right? Right, like half of a quadrant's 45, half of a half is 22.5, so it's just about a quarter, right? So I will say, you know, like here.
Why would it go up to the?
Well, this is 90, right? This is 90,
Oh.
and then this is about 25. Because we know that like half is 45, and 25 is just like around half of a half.
Which one's the, like the terminal side that you're, is that?
Yeah. This is the initial, and this is the terminal. Is everybody okay with how I drew this? when you draw yours, I'm going to require that you're also drawing these rotation marks. So you show me which way you're rotating. Is everybody okay with that? Okay. Let's do another. Sound good? So let's say we're going to do 350 degrees. First step, vertex at the origin. Second step, initial side on the positive x-axis. Now we're going to rotate. Notice which direction am I rotating every time here? Counterclockwise, turning to the left, right? Correct, I should say. To the left, right? That's not confusing. Counterclockwise, so 0, 90, 180, 270, and then 80 more. So it's like 90, 90, 90, 80. Is everybody okay with this idea? So this allows us to draw angles 0 to 360, right? Okay. What about negative? Yeah, what if for a negative angle we just turn the other direction, right? Instead of going counterclockwise, we'll go clockwise. Right? Positive angles counterclockwise, negative angles clockwise. So now we can do negative 360 to positive 360. Cool, we're really building this out. What if I want things that are bigger than 360 or smaller than negative 360? What if I wanted to do, say, 405? Okay, well, start the same way. Vertex at the origin, initial side, and we started our rotation. Which way am I turning? Counterclockwise because positive. Great. So 90, 180, 270, 360, and then like 45 more. So it just means I spin around the thing more than one time. Oh!
Oh, I was gonna ask.
Yeah, go ahead. So what have I really unlocked now? I can draw angles as big as I want or as small as I want. I just might have to spin around more than one time. Whatever, that's fine. I can do that. But we've now unlocked a way to draw and represent these angles. Is everybody okay? By the way, this is called a standard position angle where we fix the vertex to the origin and the initial side to the positive x-axis and then rotate the other terminal side about that pivot point. What do you guys think? So far so good? No big deal? All right. Let's do another example. I'm going to, on the same axis, I'm going to draw a 120 degree angle and a 480 degree angle and kind of see what happens here. And I'll color code these since I'm doing them on the same axis. So let's do, this guy's a ready, and we'll do this guy's a bluey. Yes, go ahead. All right, we were good to start. Vertex, initial side, then 120, so 90, and then like 30 more. feel okay there? Notice I'm just kind of eyeballing where these are at. My requirement for you would be like, you know, like, should it be closer to this axis, or somewhere in the middle, right? So like 30 degrees should be closer to this axis than the middle. So as long as it looks closer, you know, to that axis in the middle, you're good. Same thing if it's like in the middle-ish, in the middle is fine. If it should be close to this one, it should be, that's all I need, you know. Is it less than halfway? Good. About halfway? Good. More than halfway? That's kind of what I'm looking for visually on your papers. Okay? All right, let's do the 480 now. So again, vertex and initial side. And then we'll count here. So 90, 180, 270, 360, 450, stop, and then 30 more. And what do we notice? I notice my initial side and terminal side are in the exact same locations, even though the angles have different measures, right? One is a 120-degree angle, the other is a 480-degree angle. But if I strip away the rotation marks, the arms of the angle are in an identical location. Everybody's okay with this? This has a special name. We call these things coterminal angles because their terminal sides coincide. Right? They lay one on top of the other. If I look at the measures of those two angles, 120 and 480, do you notice anything, any relationship between those two values? It's getting steamy. Yes,
480 goes in, 120 goes into 480.
that's true, but that's not what we're looking for here. Look at the difference. If I subtract 120 from 480, what do I get? 360. So 480 is one full rotation and then 120 degrees, which is exactly what we'd expect for it to land in the same spot, right? Doing one full rotation puts us back at the start, and 120 degrees lands right where 120 is. So if I wanted to predict where another coterminal angle would be, what could I do? Add 360 to 480. And if I wanted another one after that, add another 360. So how many angles are there that are coterminal to a given angle? Infinitely many, right? Because I can just keep adding 360 the whole time. Do I have to add 360? No, what else could I do? Could subtract, right? So because angles are allowed now to be negative also, we could keep subtracting 360, and that again will generate coterminal after coterminal after coterminal. So for example, 120 minus 360 is negative 240. That angle would also be coterminal to those other two. Family.
So the coterminal, I don't really understand like how to know if it is like, does it because they stop on that arrow going down or?
So remember that this guy is the terminal side, right?
Yeah.
Notice that both angles' terminal side is in the exact same location. That's what we mean by coterminal.
Okay.
So if you look at the picture, the two terminal sides will be in the exact same place. In fact, it'll look like just two copies of the exact same angle. The only thing that'll be different are the rotation marks, right? Now, if you compare the measures, if I subtract the two angles, the difference should be a multiple of 360 degrees, which which means that they're the same thing plus some kind of rotation,
Alright, thank you.
full rotation. Joe,
What I don't understand is like, I don't get how that, they're like, go around like multiple times. Why aren't they just like that would be like a normal angle, you know, like up to 360. Like I don't really understand why the purpose, you know what I mean?
so imagine we're in like the real world and you're working on, like you're an engineer, we're working with vehicles, right? So part of the way a car works is you have like a drivetrain that spins, right? And maybe there's some spot on the part that has a flaw, and you're wondering how many times is this spot with the flaw going to rub against, you know, the inside of the casing when the part spins for like 10 seconds. Well, you need to know how many rotations that makes in there. Like what is the angle that spins? So you can, right, if you think about spinning parts now, like, go ahead, sorry. Something happening, you know, like if the rotation of that part is 720 degrees versus 360, that's meaningfully different, even though they're both landing at the same spot. One had 3 times that thing rubbed across, and the other had only 1 time it rubbed. Does that kind of make sense?
Yeah.
So this is often real important when you're dealing with things that are like spinning.
Yeah.
Is that what you're kind of asking?
Yeah, I guess.
Okay. The other way to kind of think about these coterminal angles is these coterminal angles are a little bit like equivalent fractions. So like 1/2, 2/4, 3/6, 4/8, all mean the same thing to us, right? But in some cases we need 4/8 instead of 1/2 if we have to add it to another 8, right? Sometimes when we're dealing with these angles, we need the coterminal angle because it's going to be more appropriate to deal with than the other version. But they're going to act the same because their terminal side is in the exact same location. So if we're talking about sine, cosine, tangent of 480 and sine, cosine, tangent of 120, they're going to give us the same values. We haven't gotten how to do that yet. Not important right this second, but that's kind of where we're gonna be heading. What do you guys think? You okay?
Yeah.
Do you feel good about drawing these pictures and like looking at a picture and reading the value of it? Okay, because that's what you're doing in your second class work, Delta Math. Let's look at the picture real quick.
Is this considered 4.2?
This is 4.3 CW1.
Oh.
We're in 4 point, we started 4.2.
Yeah, like I put up there.
And then we backtracked to 4.1.
Skipped over 4.2.
Well, we backtracked today,
Oh.
and now we've jumped ahead to 4.
Jumping around.
And again, because I wanted to start with the most familiar topic, which is the 4.2 stuff with the bright triangle face, which usually students remember the most. All right, I want to, before you guys dive into this, I want to walk through how you use the Delta Math to answer these questions. So I just want to look at these real quick. So this problem here says estimate the given angle of rotation within 10 degrees. So I look at this. Okay, one quadrant, it's in the first quadrant, so I know it's between 0 and 90. Everybody agree? Okay. I look at where it's at. It's less than halfway. You guys agree? Using your eyeballs? Halfway is maybe here. That look about right? So I might say this is like 35 or 40. It looks like more than a quarter, but not quite a half. So maybe I'll say 35. And it says, correct, it was close enough. The actual value is 32, but I was within 10 degrees of it either side, so it counts. That's first Delta Math, is just kind of eyeballing these. Some of them will be like, 126 degrees. Some of them could be like 309 degrees, just like. Is everybody okay with what we're doing here though? Okay, just kind of using your eyeballs and making an estimate. Here it says rotate the point 105 degrees within 10. So again, I'm going to be grabbing this yellow circle and I'm rotating. So here's 90 and then maybe 15 degrees more. I'm just kind of estimating. Again, 15 degrees is like, a third of a half. So that's probably a decent guesstimate. I say yes, it marks as correct. It said that I gave 113 degrees, which is just barely within 10 of 105, but it was close enough. Is everybody okay? And then the third set are going to be big angles where you have to do more than one rotation. So 882, so we're 90, 180, 270, 360, 450, 540, 630, 720, 810, and then 72 more. I don't know, somewhere over there probably. Let's see if that's close enough. Yep. And it said, what did I give? My answer was 882 or 881. So then 1 degree that time. Pretty good. But that's it. That's the second classwork assignment is this Delta Math for today. If you still had stuff from the first classwork to work on, you're free to go back and work on that now. This is for the last 20 minutes or so of class, you're just going to be working on finishing these two Delta Maths. And then that's it.
Don't do the one that's the September one.
You do not do the 4-3 Delta Math assignment yet. The one that says 4-3 Delta Math Part 1 or whatever, not assigned yet. Remember, Sunday's homework is the 4-2 Delta Math. We did the 2 classwork assignments today, the CW assignments. The 4-3, haven't got there yet. We still have much more to talk about here. Ruby.
For the second Delta Math, rotate it the opposite way for the negative.
Okay.
What do you think this one is? 80? Yeah.
Oh,
yeah.
I was gonna say that's great.
Yeah, I just got it wrong.
Okay. So you might have been just barely off full scroll now. It would show you before, like what you got. You got it wrong, so it's like, oh, I didn't go far enough, right? Right? So you can look at that to help you get better at estimating.
Wait, is it 4.1?
Does that help?
Sure. Yeah, yeah. It's like she done it. That's homework, right? Yeah.